that's the problem, right? Because no, that's not a problem, but that's the problem to my mind. Because a small shared memory machine is basically like just our laptop, right? So this means that we can have a MapReduce implementation on our laptop as well, and then we have a large NUMA multiprocessor. Okay, so that works, and yet another for an even larger collection of network machines. So that's purely distributed system. What I have in my mind, like hundreds of nodes. Now the thing is like, okay, so MapReduce doesn't mean that it always has to be on the distributed system. It could be even on your commercial laptops. So that's good to know that it's an abstraction over pretty much anything of any scale. It's just that we have to swap out the implementation, I guess. Okay. Section describes an implementation targeted to the computing environment in wide use at Google. Okay, so this current section just targets it for the Google, but the implementation could be possible for any kind of environment. Large cluster of commodity PC connected together with switched Ethernet in our environment. So machines are typically dual processor x86 processor running Linux with 2 to 4 GB of memory per machine. Commodity networking hardware is used typically either 100 megabits per second or 1 gigabit second at machine level, but averaging considerably less in overall bisection bandwidth. I did not get that point honestly. So commodity networking hardware is used typically either at 100 megabits per second or 1 gigabit second at machine level, but averaging considerably less in overall bisection bandwidth. Okay, so I think they are just telling the networking. I'm not. I'm not sure. I need to GPT it. Like I'm really not sure. The sentence is describing network speed inside a cluster of machines. Yeah, so I thought similar stuff, but it was it was phrased hard for me, and it's pointing out a difference between the maximum speed of each individual machine network connection and an actual bandwidth available across the whole system. Mhm. This means standard off the shelf network equipment, not expensive. This means standard off the shelf equipment, not expensive specialized high performance networking. Okay, commodity networking hardware means. Okay, so standard Ethernet switches, regular 100 Gbps. Okay, okay, okay. This refers to the network interface speed of each machine. Okay, okay. So each machine can theoretically send and receive. Okay, okay. But averaging considerably less in overall bisection bandwidth. This is the key idea. The total bandwidth available between two halves of a network if you split it into two equal parts. But okay, so that means the bisection bandwidth is the total bandwidth available between two halves of the network. Okay. If the half machine talk to the other half at the same time, how much data can flow? Even though machine might have one Gbps link, the network switch or topology may not support all machines communicating at full speed simultaneously. So individual machine 1 Gbps, entire cluster under heavy cross traffic much less per machine. Okay, so I don't need to probably understand the analogy, I get it. So the thing is they are saying, just a second, yeah. So they are saying that first of all they are using commodity hardware, so that's something I understand. They are basically using not the most top of the line expensive stuff, like they're using relatively cheaper options. And the data flows between two nodes is basically 100 Mbps or maybe 1 Gbps, so like something like that at machine level. So basically between two nodes. So basically each node can theoretically have like 100 Mbps or 1 Gbps input or output sort of speed. Okay, but averaging considerably less in overall bisection bandwidth. Okay, so this means that all bisection bandwidth basically means that if we take the cluster and divide it into two, and the one half is used to talk to other half, then the average could be considered a little bit low on the lower side than this because of the load and all this stuff. So basically, they are saying that not always we are up to the 1 Gbps speed. It could be a relatively lot lesser if we are involving the whole cluster. I think that's what they means, right? Mhm. A cluster consists of hundred or thousand of machines, therefore machine failure are common. Yeah, so that's something we have to take care of. Storage is provided by inexpensive IDE disk integrated development environment is not sure. I need to check what IDE means here. Attached directly to individual machines. Okay. A distributed file system 8 developed in house is used to manage the data stored on these disks. The file system uses the application to provide availability and reliability on top of unreliable hardware. Okay, let's see. Storage is provided by. First of all, what does this mean? I need to check. There's a lot of things I need to check. But that's the benefit of reading each line by line, right? So I just don't like. If I would have skimmed it through, I might have understood what I have given the recap in the start of the video. But like since I'm reading now each line word by word, I tend to understand it deeper, right? So let's go back to the video. So the sentence is describing how storage is set up for distributed system or cluster. Okay, so the IDE this means integrated drive electronics are older low cost hard drives. Okay. The consumer grade not high end enterprise storage system. Okay, makes sense. They are cheaper but less reliable or slower than specialized hard disk storage hardware. Okay, okay. Attached directly to the individual machine. That each individual machine has its own local drive. Yeah. So basically, what they mean is that pretty much each machine contains some sort of older version, lower or cheaper priced hard disk and attached to each machine. Okay. A distributed file system developed in-house is used to manage the data stored on these disks. Okay, so yeah, they have a distributed file system that manages this stuff, these data on the disk. A file system used the file system uses replication to provide availability and reliability on top of unreliable hardware. Okay, so basically what they mean is that the distributed file system that they have developed in-house is used to manage but also provide the availability and reliability of this cheaper hard disks that have been attached to the machines and their data. Okay. User submits job to a scheduling system. Each job consists of set of tasks and is mapped by the scheduler to a set of available machine within cluster. Okay, so user submits a job, okay, and that scheduling system, each job consists of set of tasks and is mapped to a scheduler is mapped by the scheduler to set a available machine within the cluster. Okay, so what they mean is pretty easy that user can submit a job to the scheduling system. Job is pretty much what we think it is, like it runs some sort of task. Like the scheduler takes the job and map it to the set of available machine within the cluster. That's it. And once everything is free, that job or set of tasks will be running. Okay, easy peasy, I guess. Execution overview. The map invocation are distributed across multiple machines by automatically partitioning the input data into the set of M splits. Okay, so let's just say we have the map invocation. It will be distributed across multiple machines and it will be partitioned into M split. The input split can be processed in parallel by different machines. The reduce invocation are distributed by partitioning the intermediate key into R pieces using a partitioning function. Example hash key of mod R. The number of partitions and the partitioning function are specified by the user. Okay, so I think I understood a little bit, not all. So let's recap. So first, that the map invocation, basically the map function, is distributed across the multiple machines, and like we have the input, so we basically what we do is we take the input data and split it into m splits, and that can be done automatically. So let's just say we have some data, it splits, and then we run it parallelly to different machines. So that split, we have some, let's just say, data, it then splits, and then we map it to different machines and we run it on different machines. Okay, once that m splits has been run parallelly, and I think there should be no issue running it parallelly, because then, like, if we do it sequentially, what we will do it, we will take a single input, run the map function on it, run on it, and then produce output, right? So, and then when we have, let's just say, another input, we take it, we run the map function again, and then we have the output. So like if we even do it sequentially, there's no interdependency between one input of or the another input. So basically, if we do it sequentially, it will be a lot slower, but if we try to parallelize it, since there's no dependency of one input when running on map function to another input when running on map function, we are good to have it split in multiple chunks and parallelize it, because there's no interdependency, so it won't be causing any some sort of consistency or some sort of dependency issues. Now the story for the reduce function is completely different, right? Because now we, let's just say, we have intermediate functions. So now, not intermediate function, basically intermediate keys. So intermediate keys, what reduce function generally do is take the similar intermediate keys and I don't know, like collectively take it and do something on it, right? So now there's a dependency of different intermediate keys, because one type of intermediate key, let's just say we want to run, let's just say we have intermediate 1. So if we have intermediate key 1, we will want all of the intermediate key 1s to be collectively present, and then we run reduce function on it, right? So there's an interdependency of multiple intermediate keys, because we want to group all the similar keys. So okay, that makes sense. What they do is intermediate reduce invocation are distributed by partitioning the intermediate key spaces into R pieces. Mhm. Using a partitioning function. Example, hash of key or hash of key mod of R. The number of partition R and the function key are specified by the user. Okay. So let's just say we have the intermediate key. We have a lot of intermediate keys. Some are same, some are not. Like I don't know. And we take the space and we want to, let's just say, uh, split it into R pieces or partition into R pieces. So one of the strategy could be that we take the hash of the key and mod it to R. Mhm. Okay, so basically they're saying that, if you think about it, partitioning function here is nothing more than a way to say that, okay, we have all the intermediate keys. Now how we want to group it by, right? So in this case, the example they gave is hash of a key mod R. So let's just say let's just say R is 10. So if we want to partition into 10 respective splits, so we can just take the hash of the key and mod it through R. So what it will do, it will basically uh, take it will group by all the keys in a particular R which have similar reminder when divided by R. So that's how mod works, right? So they are basically, it's a strategy of grouping by intermediate keys, but at the same time trying to partition it. Well, obviously, like partitioning will make them group by somehow, because let's just say if I have a long chunk of space and I partition it, so obviously some sort of space will be partitioned to one partition, then we have another partition. So we can say that this is a one group and this is another group. Okay. The number of partitions are and the function keys are specified by the user. Okay. So basically the strategy to group or to partition and how many partition, how many grouping could be there is defined by the user. The another question I have is like, let's just say I want to partition it based on the keys that all just take all the keys that are similar and sum their values. This is something which I want to partition. It will require me to write a partitioning function in a way that I can group by all the keys that are same, right? So I think like hash of key mod R is pretty good example. Let's just say I want to mm, oh no, that's correct, right? So I'm not sure, like let's just say I want to divide the space into R pieces, because this is something which I have to think, right? So I take like 10 and I do the hash of key. So all the keys that are similar, all the keys that are same, they will be automatically going to same partition, because that's how hash work, hash and mod work. Okay, so basically we are pretty sure that if we do hash of key mod R, the keys which are same, they will all lie in the same partition. Addition to that, there might be in a single partition, there might be some extra keys which could be similar to the other keys, right? So similar in way that once divided by R, they have the same reminder. So in this way, let's just say if I take the single partition and run a reduce invocation on it, if I'm going to sum all the values based on the same key, there's no issue, because I know that for each of the partition, if there is a partition, in a partition, if we have a key, we know that it will this partition will contain all the instances of that key, and obviously the similar key, and the similar key will have all of its instance as well. Okay, I mean that's a bit confusing. I'm not sure like I can whether I can explain it without the diagram, but yeah. hmm Figure 1 shows the overall flow of MapReduce operation in our implementation. When the user program calls the MapReduce function, the following sequence of action occur. The numbered label in figure 1 correctly represents. Okay. Okay, so now let's read it. The MapReduce library in the user program first split the input files into M pieces of typically 16 megabyte to 64 MB per piece, controllable by the user via operational parameter. Okay. It then starts up many copies of the program on clusters of machine. hmm Okay. So basically, they take the user program, split into input. The, wait, what? Library in the MapReduce library in the user program first split up the input file into M pieces of typical. Okay. It then start up many copies of the program on cluster of machines. I did not understand this, but I understood it that says that MapReduce library will split the input files, like partition it into different pieces. So basically they are talking about this, that user program will split the library inside the user program will first split the input files into different partitions. I will try to understand this line a little later. One of the copies of the program is special, the master. The rest are workers that are assigned work by master. There are mmap tasks and R reduced tasks to assign. The master picks the idle worker and assign each one of the map task or reduce task. Okay. So main actually story starts from the user program only. So user program must have downloaded the MapReduce library, which basically takes it. It basically gets forked, and one of the fork is master. So we will talk about master later. One of the fork is probably used to divide the to partition the input files, I guess. Okay, right. It also then start up many copies of the program on cluster of machine. Okay, so there's no forking involved till here. So basically we have the MapReduce library in the user program. It splits the input file, uh, partition it, and that's it. Okay, right. So got it. So basically this is split automatically by the library in the user program, and we don't have to do anything. Also, that library itself take the it makes sense. Like, now that I think about it, it's obvious. So it will take the, so we, let's just say we install the library, right? So it will that library will split or partition the input file as well. It will also make different fork of the user program we have written. One of the fork is going to be the master. That's good. One of the copies is special. The master, the rest are workers that are assigned work by the master. They are a map task and R task to assign. The M is basically the partition of the. This basically M is the number of workers we have in the map for the map task, and R is the number of partition we have for the reduced task. Okay, so the master picks up the idle worker and assign each one of the map task or reduced task. Okay, so this basically these splits will be splitted to different workers, and master will take, which master will come up here and say that, hey, now this is idle, you can just whatever the fork we have written, we have created here, could be could start working. Then they'll just, let's just say this one is this one is also free. Master will say, hey, get your split and read your split. Oh, okay. So yeah, first is basically fork, like they said. First is basically the fork, like they said. Then master will assign different map from the user program to these different workers. Once these workers are available, they will read the split that they have been assigned automatically, and they will work. A worker who is assigned on map task reads the content of the corresponding input select. Yeah. It parses key value pair out of the input data and passes each pair to the user map defined map function. Yeah. So yeah, it's basic stuff, right? So that basically now the worker will take the key value will pull the input split. It From the input split, it will take each of the key value pairs and it will pass the key value to the map function. The intermediate key value pairs produced, just a second, I need to make it a little bigger more. The intermediate key value pair produced by the map function are buffered in memory. Yeah. So they are basically buffered in memory and later probably written to local disk, local write on local disk. Periodically, the buffered pairs are written to local disk. I know the reason, because if they probably write each of every pair the moment it was created to the local disk, it will be just too much writing into the disk, which will make this process a lot slower. So what I guess they do is they let the map function run a little bit, have have some sort of intermediate key value pairs in the buffered memory, and then they flush it out to the local disk. I think this is standard practice in some sort of databases as well, right? Now, once they are flushed, the location of these buffer pairs on the local disk are passed back to the master. Okay, sorry, I missed this line. Periodically, the buffered pairs are returned to local disk, partitioned into R region by partitioning function. Okay. Once we have it written on the uh, local disk, we will take this local disk. It will be partitioned. It will be partitioned by whatever the user function returns. I think this is also should be done by the uh, library of the MapReduce as well. Okay. The location of these buffered pairs on the local disk are passed back to the master, who is responsible for forwarding these location to the reduce worker. So okay. So this means that uh, that the space, the local disk space in which these writes are flushed to, they are passed They are partitioned. Okay, they are partitioned. Yeah, they will be partitioned once we have the writes flushed in the local disk. Then they will be partitioned, and then each of these locations is passed back to the master, and then that master also tells that worker that hey, this is the location. When a reduce work is notified by the master about this location, it uses RPC to read the buffer data from the local disk of the map worker. So yeah, so it will basically do is it will do a RPC remote procedure call, and it will remote read the local writes written by the map invocation. Got it. When a reduce worker has read all in the intermediate key, it sort. Okay, now this is interesting. When a reduce worker has read all in intermediate data, it is sorted by the intermediate key so that all occurrences of the same key are grouped together. Okay, makes sense. The sorting is needed because typically many different key maps to the same reduce task. If the amount of intermediate data is too large to fit in memory, an external sort is used. Okay, so this is basically what they are saying, right? It's similar to what I said that uh, that are basically that a reduce partition should contain same keys but just grouped together. Now they use sorting. Now they use sorting, which will probably like have all the occurrences of the same key, even grouped together one by one, basically in a chunk. Mhm. I believe that this means that the reduce function that the user write, they have to write it under some constraint, right? Such that these type of grouping is possible. Like if a user writes some sort of random function which by any means does not allow any kind of grouping of same keys or like similarity, mm, does not allow any kind of grouping between similar keys or same keys, then that is effectively not a good reduce function, and maybe MapReduce library will not be even allowing it. So I'm not sure, like, but I think user has to write some sort of reasonable partitioning function, because that is the only way that we can have similar or same keys grouped in a single worker. Mhm. Yeah, like I said, sorting is required because different key maps to the same reduced task. If the amount of intermediate data is too large to fit in memory, an external sort is used. This one is easy to understand. Reduce worker iterates over the sorted intermediate data, and for each unique intermediate key encountered, it passes the key and the corresponding set of key values to the user reduce function. The output of the reduce function is apprehended to the final output list for the reduce partition. Okay, so this one makes sense. Basically, since we have sorted intermediate keys, the reduce function will just iterate over it once, just find the unique key. It will take all of the values for that particular key and pass it to the reduce function. Reduce function will then write it to the output, and yeah, the same process going on. It's almost like O of n pass that we are doing a single pass for everything since we have sorted the intermediate key data. So you see some sort of data structure algorithm problem with this. So they have basically some keys, some set of keys, and they want to ensure that uh, they group the keys, all the same keys, and their value and pass it to the reduce function. So they did what a very standard practice is, that they sort the key and then did a single iteration on it. When all map tasks and reduce tasks have been completed, the master wakes up from the user program. At this point, the reduce function call in the user program again back to the user code. Okay, yeah, so they write it and then that's the output file. Okay, easy. After successful implementation completion, the output of the MapReduce available execution is available in the R output file. One per reduce search, which with file names as specified by the user. Typically, if user do not need to combine these R output into a single file, they often these they often pass these file as input to another MapReduce call or use them from another distributed application that is able to deal with the input that is partitioned into multiple files. Okay, so makes sense. Since they're working on distributed problem, I am assuming that whatever the next step they are going to use, it will have the capability of handling a single input partitioned into multiple files. Mhm. Master data structure. So yeah, I think like not only this is a problem of distributed system, it also utilizes some concept from data structure. Like this is like taking the keys, sorting it so that the all the same keys are bundled together. Then we can just take the values and push it to the reduce function. So this is one of the concept of data structure, right? The map keys several data structure for each map task and reduce task. It stored the state. Okay, so they are talking about the data structure that is used internally by the abstraction. It stores the state idle, in progress, or completed, and identity of the worker machine for non-idle task. Okay. For each map and task and redo task. Okay, so basically they are saying that that for the map for different map and reduce tasks for different workers, they have master data structure which not only stores the state but also the identity and all the metadata required to make this implementation complete. The master is the conduit through which the location of the intermediate file region is propagated from map task to reduce task. Therefore, for each completed map task, the map master stores the location and the size of R intermediate file region produced by the map task. Update to this location and size information are received as map tasks are complete. Information is pushed incrementally to the workers that are in progress to reduce tasks. Okay, so they are saying that this data structure is responsible for propagating also the location of the intermediate file. So once the map task is complete, the master data structure stores the location and size of these intermediate files, and then it incrementally pushes it to the reduce tasks which are in progress.